Hi everyone, my name is Amira and I'll be your tutor for spec. So we'll start with statistical inference, which is the last topic. And I'll start with the purpose because that's pretty important. The point is to infer from a population. So let's say we have a population and we don't know what it looks like, but let's assume that it can be modeled with some sort of curve like this. So x here is just a random variable of some sort. Now I'll go to expected value because it doesn't get touched upon, but understanding it is pretty important. So the expected value, you can just call it the mean, but that's just the sum of the value x multiplied by the probability when the random variable is equal to x. And then variance is the sum of the squared distances from the mean times the probability that x is x. Now this is a whole lot of notation, but understanding it is kind of crucial because that's where all of sample means and the distributions come up. So expected value, that's pretty intuitive. You're just finding the mean, and this is for a discrete distribution. So in spec, we normally deal with continuous functions. The whole deal with variance is that you can think of variance as the expected squared distance from the mean. Why is that? Because you're simply replacing, let's say, this x with this argument. So essentially, the variance is the same thing as the expected value of this argument right here. You're just subbing it in. And that really tells us something. It's trying to find the average spread from the mean. So from all the data points, what is the average distance from the mean? We have data points like just in a line. If this is the mean, then we take all of these distances, we square them, and then take the average. Why don't we use the absolute value? This achieves the same thing. But the reason we don't do that is because it's not differentiable. That's why we use the square. So that means that this is defined in a way that we calculate the variance first, and then we can get the standard deviation, because that is just the square root of variance. Right, I'll go over a couple of properties. It's a bit of a lengthy intro, but these fundamentals are pretty important. We'll start with expectation, having this property called linearity, which means that if you have a random variable x, and then you scale it by a factor, and then add in a constant, you can treat it like algebra almost. Why is that? We can go through the definition. So we sub it into the formula, and we can distribute. Well, we know for any probability distribution that the sum of all probabilities is 1. That's how it's defined. And we know this is just your regular expectation of x. So this just becomes this expression right here. And also we have this property where basically if you take the sum of any two random variables like this, because of its linearity almost, we can split this apart. So we get this property, which does make sense because let's say we have two distributions, x1, and then we have x2. We take the mean here. If we add them together, we get some curve like this. We can decompose it into its individual parts and then add up the mean. And with variance, if we try the same thing, right? We scale it up by a factor of a, then we add on a constant, b. The effect of this is different to expectation. It's different to the mean. It instead scales it by a factor of a squared. And b doesn't actually affect it at all. Why does this occur? Well, if we take x1, for example, imagine we apply transformation, we dilate everything, and assume, in this case, that a is bigger than 1, so then it will stretch it out like this. It's like your function transformations. You're essentially just dilating the distribution in the x-axis. And what this does is, notice every single point. This is continuous, but imagine discrete for a sec. But before the distances were different. And now we scaled it up by a factor of A. And because of that, because variance has this squared term here, what this does is it squares the effect. The spread gets multiplied by a factor of A squared. Now, what if we try to tack on a B at the very end? So then you get AX plus B. Well, if we shift the distribution by constant B, so this was the old one, and this is the new one. We're simply shifting it by a constant B. Well, this doesn't have any effect on the relative distances, right? Because everything gets shifted by B. So it does nothing. The variance stays unaffected regardless of what B is. Okay, I see in chat example of a random variable. Okay, you can do that. A random variable is just a uniform variable on the interval 0, 1. So it's just from 0, 1, it has a value 1 all the way. And what this means is when we dilate it, let's say by a factor of 2, then it gets stretched from 0 to 2. And so the variance gets scaled by a factor of 2 squared, which is 4. That's how it is. With discrete, you can do it. It's a bit difficult to visualize than continuous. But in spec, it will be continuous, the kind of distributions that you'll be dealing with. So back to this. This also applies to variance as well, as long as the events are independent. Okay, so what's the point of this? These formulas won't come up, but really understanding how these two so-called moments, mean and variance, how they get affected under certain transformations. That's what statisticians use and exploit with distributions. Now let's get back to the context. Okay, so imagine you're a statistician, right? And there is a population, as we said here earlier. We said that X was a population, right? But in reality, when you go around and let's say you want to interview the whole population, you want to get data, right? Now, that doesn't work all the time. Surveys done by like private groups, they operate on samples, which is just a subset. So the whole point of what I'm trying to get to is that since we only take a sample, how can we be sure that the results we get is actually accurate and reflects the population? For now, I'll assume that we know what the distribution of the population is. We know what the shape of it is. Let's just say it's this normal curve that we got. Okay, I go around and I take a sample. So I'll call it S, and then it will be the set of points x1, x2, x3, so on, and xn. This is just the event of taking a measurement. So it could just be me going to a house, interviewing them, getting some piece of data on a survey. And we have n of these points because we can't cover the entire distribution. So we take n samples or n points in a sample. And this is the sample size. Now you might also see capital N. Capital N refers to the population size. But in Specialist, you'll be dealing with lowercase n because that refers to your sample. I go around and what am I interested in? The mean, because the mean tells a lot. And I can't tell anything from a single data point. Like x1, capital X1 is not gonna tell me much about the original distribution, because what if x1 was here? What if x1 was here? It doesn't tell me anything. So I take the mean. Okay, I define the mean as capital X bar. It is the sum of all of the points that I just took all the way to x of n. And we divide by n because we have n points. And I want to know, what am I expecting from this distribution? So remember, this is different. This is a sample, and I want to know the distribution of the sample mean. What I'm asking myself is, if I go around the sample, I do it several times. Let's say I go to some suburb in the south side, do a survey, north side, do it again. Same sample size in multiple places, so I repeat that same sample. And I want to know how that sample mean looks like on a graph, right? Maybe we get the first sample mean here, then here, 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 and it gets clustered, so we get something like this. I want to know how that distribution looks like. How do we expect what to know? Well, we can use the expectation function. We're just going to plug this whole expression in and put it right here. And I want to know, what am I expecting? What is the mean of this distribution of sample means? As we discussed earlier, we can split any sum of random variables. So we can go e of x1 on n plus e of x2 on n, all the way down to e of xn on n. We notice that there is an n in each of these expectations, so we can factor out an n from all of them. Right. Now we ask ourselves, what is the expected value or the mean of each of these? Well, remember, x1 was the process of taking a data point from the population. So that means assuming our sampling method is not biased in any way, we're not considering like a small subset of the population, then if we do assume that there is no bias, then the distributions will essentially be the same, because it's like we're handpicking from the population at random. There's no bias. We're not just targeting like rich households. So let's say I'm doing a survey on the cost of housing, and if I go up into like Hamilton or Northgate, it's going to be some bias as we're going to target towards the upper end. But in this case, theoretically, these should be all equal to expectation of x. And we have n copies, right? Okay, these n's cancel. So then we just get left with the expectation of x. I mean, it's intuitive because we define the distribution as the mean of the sample. So obviously the mean should just be itself. This is from a purely theoretical point of view, assuming our sampling is not biased. We can do the same thing with the variance. Same thing, we can split up the variance all the way until we have x of n on n. We scale by a factor of 1 in n. Well, it scales by a factor of 1 in n squared then, right? So then we plot the 1 in n squared across all variance terms. So then we get x1 all the way up to xn. Again, like last time, assuming our sampling is great, this will just be n copies of the population variance. Okay, simplifying, we get the variance of x divided by n. We prefer the standard deviation. That's what we use and express. The standard deviation of the sample means, this is capital X right here. So this is our new distribution where we're taking the mean of the entire sample. This will simply be the square root of this. We get this simplified form. This was the standard deviation of the original distribution. So if we assume that the distribution had a standard deviation of sigma, then this is it. So then when we take our sample, we call it S of the sample means will be this on root n, and our mean will just be the population mean. But remember, this will be approximate. Here we used capital X. Why? Because we derived it from the population, but in most questions, remember that we don't know what the population distribution is. We're taking a sample from the population, but we don't know what it looks like. When we refer to sample, we use lowercase x. These refer to actual values, like your experimental. If we compare the population, you will see capital X, you will see capital N. They'll refer to the population count. You'll see mu, you'll see sigma. So x is your random variable representing your distribution. N will be the number of data points in your population, mu is the mean, and sigma is the standard deviation. If we go over to the sample, the distribution is capital X with the bar. This represents the distribution of the sample means. The mean will just be little x bar. Little n, we have little x bar, and we have s of x. Or we can just put s. Putting an x down there indicates that it's for the sample. This is for the sample, right? So I'll just remove this. So this is purely the sample. And then when we take the distribution of this, so remember these values refer to a single sample. And then when we analyze its distribution, the mean will stay the same, right? But then the standard deviation of this will be the sample divided by root n. Again, here we assume that our sampling methods are good enough so that the sample mean is roughly equal to the population mean, and the standard deviation of the sample is roughly equal to sigma. So this is the gist of it.